Guys, I'm gonna be walking through problem set 6 for Dr. Santos. Just share my iPad. If I can figure out how. Okay, there we go. So I'm just gonna. All right. So first thing here that I notice is the 5, 2, 1 for the integration of the peaks. So I'm just gonna go ahead and write that out on top of the peaks themselves so that it's easier to visualize everything. And then the first thing I do when I start these problems, especially since you're given a molecular formula, you can easily just calculate the du. So that's going to be, there's 7 carbons minus half the hydrogens plus 1, and that's going to give you 4. And then this is really nice because this du of 4 just tells you right off the bat that it's going to be aromatic. And you can look over here on the NMR and see these 5 hydrogens. And the only thing that that could be is a monosubstituted benzene, because that's the only way to get these 5 hydrogens equivalent to each other. And then I'm going to go ahead and make an integration table. This is something that I do for every problem, just because it makes it easier to keep track of all the different pieces of the puzzle. And then it's easier to assemble the molecule after. So like that. And then we know this 5H already is going to be that benzene that's monosubstituted. This 2H is going to be a CH2. And then this 1H, if you look at the formula, you see there's 1 oxygen. And we know the du is 4, so it can't be a carbonyl because we already have all 4 degrees of unsaturation taken up by this benzene right here. So the only thing that it could really be is an alcohol, because that would correspond with this 1H peak right here. And then now we have all the pieces of the puzzle, and we can just go ahead and assemble them. There's really only one way to put it together. Like that. And the next one's pretty much the same idea, except if you notice the integration of the peaks doesn't match up with the molecular formula because there's 4 hydrogens here, but there's 12 hydrogens in the formula. So that just means that this is a ratio. So all you have to do, I'm going to make my table again. Multiply by 3 because that will give you 9 hydrogens plus 3 hydrogens, which does equal 12. And then this 9H here, this, like most of the time, I would say all the time, is going to be a tert butyl because that's the only way to get 3 methyls equivalent to each other. So I'm just going to write tert butyl like that. It's faster. And then this is going to be a methyl. And then that only gives us, there's 4 carbons here and 1 carbon here, but we have 6 carbons in our molecular formula. So let's go ahead and calculate this du, which is going to be 1. And then that tells us we need a double bond or a ring somewhere. So we have this oxygen, and then we're missing a carbon. So that is going to be our carbonyl because it will get us to 6 total carbons and then also incorporate the oxygen with also giving us that 1 degree of unsaturation. So I'm just going to write my carbonyl like this. And then now that I have all the pieces of the molecule, I can go ahead and assemble them. So I've got the methyl, carbonyl, and then I've got the tert butyl right here. And we can double check, make sure the amount of hydrogens, there's 9, 12, and then 1, 2, 3, 4, 5, 6 carbons, and then our 1 oxygen. So that's going to be that one. And then this one, again, same idea. I'm going to go ahead and calculate the du. So 3 minus 3 plus 1 is going to give us 1. And then I'll make my integration table. And and this is 2 to 1. And again, we notice that this doesn't match up to the molecular formula, so I'm just going to go ahead and multiply these by 2, which gives us 2H and 4H, which does equal the 6 total that we have. So this is going to be our CH2, and then this is going to be 2 CH2s. And then we've also got this oxygen and a DU of 1. So we only have 3 carbons, and we have our 3 carbons already right here. So we can't add another carbon to make that carbonyl. So we know that's not possible. And then the only other thing that we could get is a ring in order to incorporate that oxygen. And that would also give us these 2 equivalent methanes here. So if we draw a ring like this, we have these 2 right here, and then this one methyl or methane, methylene, sorry, right there. And this is a tricky one because it's not usually your first instinct to make a ring like this. But this is a really good question. And I've seen it a lot of times. When I took the class, it was on the exam. So yeah, keep an open mind for these sorts of problems. Don't just assume that it's not going to be a ring. And it has to be a double bond because there is a chance it could be a ring like this molecule. All right. So next question. This is just chlorination. And then the chlorine here, that is going to be an ortho-para director, if you guys remember to Unit 1. So that means we could either have an ortho or we could have a para. So I'm just going to draw them both here. And the reason I put the ortho at 66% is you might think, oh, the steric strain from this chlorine might get in the way, making it less abundant. But because there are 2 ortho positions for the nitro to add to, there's a higher chance of this being ortho than para. And the steric strain isn't really that important from this chlorine just because it's so small. Now, if this were a tert butyl or a bigger group like that, then the steric strain would come into play. But in this case, just because there's 2 ortho spots as opposed to the 1 para spot, it's more likely to be in the ortho conformation. And then this is just going to be our SNAR reaction, which requires, remember, this nitro is a very strong deactivator, and there needs to be a strong deactivator, deactivator ortho para to whatever the leaving group is, which in this case is the chlorine. So it just replaces that chlorine with this OCH3, and then this is what we get. All right, synthesis. So synthesis can be a little intimidating. I like to break it up into pieces. So the first thing I see here is we've got this carboxylic acid, and I want to be able to put that on the ring pretty easily because the carboxylic acid is a meta director, and conveniently this alcohol here is already meta to it. So as long as I can get this carboxylic acid on the ring, I can pretty easily add the alcohol after that. So the first thing that I'm going to do is Friedel-Crafts acylation, which is another one of your Unit 1 reactions. So that's going to be like that. So we got this on the ring. And I know that there's a way to, if you guys remember the benzylic oxidation reaction, which gives a carboxylic acid on the benzylic carbon, which is this one right here. All I have to do is get rid of this carbonyl to be able to do that reaction. So I'm just going to reduce it with H2PD on C. And then we've got this, and then I can do that benzylic oxidation, which is H2CrO4. You can also do KMNO3, KMNO3. Let me double check on that one. But this will give us the carboxylic acid. And then 1 second. Sorry. Okay, sorry about that. Where was I? So, okay, the benzylic oxidation. Right, so this is the H2CrO4 or the KMNO4. Just drawing a blank on that one. Either one works with heat. And then now that we've got this carboxylic acid, we want to be able to add this alcohol. So the only way that we know how to do that right now is through the diazonium salt reaction. So the first thing we want to do, oh my gosh, is nitrate it. And then reduce that to an amine. And then we can do HONO, which if you remember, HONO is this. But if you were to do a synthesis, it's fine to just write HONO like this, but you should be able to recognize the full thing written out if you have it on the reaction sheet or something, but just doing synthesis, it's fine to just write HONO. And that turns this into the diazonium salt. And then H3O plus with heat turns that salt into the alcohol. Oh my gosh. Ah, there we go. All right. And there we go. Obviously, there's multiple ways to do this. Most synthesis, you can do it in a few different ways. This way just seems the most logical to me, but that doesn't mean there's another way you could do it that's wrong. As long as you like follow, you know, all the reactions, you follow all the correct rules and everything, there's multiple ways to do this. All right. So compound A, let's look at the spectrum here. So we can see right away that this isn't fully carbon and hydrogen. This is going to be, there's going to be another atom in there somewhere. So we're just going to do 39.76 of carbon. We divide that by the molecular mass, which gives us 3.31. And then let's see, hydrogen was 7.34%. Divided by that molecular mass, that gives us 7.27. And then we have 52.9% of an unknown. So I'm going to go ahead and divide this by the smallest number, which gives us 1. And then this is 2.2. And then this is 16. So you might see this and think, oh, 16, that's going to be an oxygen. But if you look at the IR, you can see there's no oxygen present in this spectrum here. And you can also see the hydrogen is a 2.2, which you don't want a decimal like that because you can't have 2.2 hydrogens in your molecule. So what I'm going to do is multiply this. This is going to be 5 carbons. This gives us 11 hydrogens. And then this gives us, oop, this, which corresponds to bromine. And then that way we can get our molecular formula, which is going to be C5H11Br. And you can always go back and double check your work the same way as you did here. You just multiply 5 times 12.01, 11 times 1.01, and then the bromine by its molecular mass. And that should, oh, well, I guess you don't have the molecular weight, so that wouldn't apply to this one. But if you did have the molecular weight, that's a way you could check. All right. So this IR, like we said, there's no oxygen present because there's no OH peak, and there's no carbonyl peak, and there's no C single bond O peak. So I'm going to go ahead and just move on down to this NMR here because usually the NMR gives you a little bit more information. So let's see. Make my table. Going to be 0.9. 1.7, 1.8, 3.4, and then 6H, right, okay, and then 1H. All right. So this 6H here, and we can make sure this matches. We have 6, 7, 8, 9, 10, 11, 11 hydrogens. Perfect. So 6H going to be two methyl groups, because that's a way to get the 3 or 6 hydrogens equivalent to each other is from 2 equivalent methyl groups. And then these 2 H's here are also going to be the CH2s. And whenever I'm doing this, I always like to show how many connections these things have. That way it's easier to piece it together. I know that this CH2 is a middle piece, this methyl is an end piece, and stuff like that. So this is just going to be a CH, because we know there's no oxygen in the molecule. The only thing left is our bromine, which is this. And then our carbons, we have 2, 3, 4, 5 carbons. So now we can go ahead and try to assemble this molecule. So I'm going to go ahead and start with this CH, just because I know it's a middle piece. It's easier to attach things to the middle. So we have these 2 methyl groups. We know they have to be end pieces. So I'm just going to go ahead and add them here. And we can double check our work after. I'm just going to start with the structure. Got these 2 CH2s that are not equivalent, so we can put them next to each other like that. And then move this down here. The bromine. So this is just an idea of a structure that it could be. I can double check that this is right by looking at the spin-spin coupling, which is like the singlet, doublet, multiplet, all of those. It's the splitting. So this 6H peak here, this is a doublet because we've got these 2 peaks. These right here, it's stated for us that the right one is an M9 and the quartet on the left. Sometimes it is hard to read them. Usually if you see a lot of peaks like this, you can just assume multiplet. And then if it's very confusing, she'll specify like M9, stuff like that. Usually it's pretty straightforward though, like this is 3 here, that's going to be a triplet. So these 2 methyls here are the doublets. So if you remember, the spin-spin is the hydrogens attached to the neighboring carbon. So this methyl here is a neighbor to this, and this has this 1 hydrogen here. So that's going to give us a doublet peak, because an easy way to think of it is just the amount of hydrogens plus 1. So there's 1 hydrogen plus 1. That's a doublet. That matches up. Over here, the CH2 peak, this one was a quartet. So let's see. It's got 2 here, 1 here. So that's 3 plus 1 is 4. So that one's a quartet. Perfect. And then this CH2 was a triplet. We've got these 2 hydrogens here. 2 plus 1 is 3. Triplet. That works. So that's just a way to double check, make sure you got the right structure, because sometimes in these combined specs, you guys will notice that you've got different ways you can assemble each like piece of your puzzle. It doesn't necessarily mean it's right just because you have all the pieces there, because this spin-spin coupling will tell you exactly how it's supposed to piece together. And I didn't need the carbon NMR for this one. You can look at it, but I usually just use it as like a fact checking, make sure I have the right amount of carbons. So I've got these 2 methyls are equivalent, so that counts as 1 peak, and then 1, 2, 3 carbons right here. So that should be 4 peaks total, and we've got these 4 peaks total, so that matches up. All right, so just write this down on this page. Oh, and the du, that's going to be 5 minus, and then there is the halogen, so half the halogens plus 1. Because if you remember, the formula for the du is carbon minus half hydrogens minus half halogens plus half the nitrogens plus 1. And there's no nitrogens, but there is a halogen. So don't forget about that when you're calculating the DU because we don't use oxygen in the DU, so sometimes it's easy to just like not worry about any of the other atoms and just do it based off the carbon and hydrogen. But yeah, don't forget about this bromine here. So that's going to give us a DU of 0. And then we've got the structure. And then that methyl right there. All right. Next problem. Okay, so this one did give us the molecular weight. So the first thing I'm going to do is the rule of 13, which is just dividing the molecular weight by 13. And then that gives you 8.77, but you don't want those decimals. You find the remainder of it. So you're going to get 13 times 8, which gives you 104. And then 114 minus 104 is 10. So this is the remainder that we add to the amount of carbons that we found. So this is the carbons, and then 10 plus 8, 18 hydrogens. So from this, we get the molecular formula C8H18. And looking at this, we can see this adds up to 100. So this is going to be our formula. We don't have to worry about any other atoms in here, which is nice. So looking at this, draw that line at 3000. There's nothing to the left of it. All we really see are just these sp3 CH stretches here. So again, I'm just going to go on down to this proton NMR and make my correlation table. So it's going to be 0.9 and I guess 0.95. They're pretty close to each other. This one would be like a 1.2 and then like a 1.7. All right. I've got 9H, 6H, 2H, and 1H. And this should match up. We've got 9, 15, 18. Okay, perfect. So that matches up to our 18 hydrogens. Again, this 9, that's going to be our tert butyl. And then the 6H is going to be those 2 methyls, 2H, CH2, and then CH, just like that. And let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. So this is the entire molecule right here. All we have to do is put it together. So let's start with this N piece, which is the tert butyl, because we know that has to be an N piece. And then we can either put the CH2 or the CH. So let's do CH2, and then we can just double check our work with the spin-spin coupling. I'll just write it all out so it's easier to see. And then we've obviously got that carbon right in the middle there. All right, so that's 4, 5, 6, 7, 8 carbons. And then let's see, this is a singlet peak. This is a singlet peak, doublet, and then this is just going to be a multiplet. So the 9H was a singlet, and these are all next to a carbon that has no hydrogens. So 0 plus 1 is a singlet. That works out. This right here is neighboring to a carbon with 1 hydrogen. So this is going to be a doublet, which does match up to our doublet. And then we've got this one neighboring 3, 6, 7, 8 hydrogens. So this is going to be our multiplet. And that should match up. Yep. Multiplet here. And then these 2 methyls, I believe for a singlet. It might be a doublet. Let's see. Yeah, these are definitely going to be a doublet. It's a little hard to see on the spectrum, but everything else matches up, so there's really nothing else that it could be. Um, but yeah, let's write this prettier. All right, and then the carbon NMR got 1, 2, 3, 4, 5. And then we've got 1, 2, 3, 4, 5. So that matches up these, because remember these 3 methyls are all equivalent, as are these 2 over here. So we've got 1, 2, 3, 4, 5. And that works out. Let's go ahead and rewrite this. So what was it? CH18. And then du 8 minus 9 plus 1 is 0. And then the structure was, I think, like, all right. Okay, so last one. This one, right off the bat, I can just look at this and I see this giant OH peak right there. So I know there's going to be an oxygen in there somewhere. So looking at the molecular weight, I can already assume that the missing is going to be an oxygen, just because I see that peak. So let's go ahead and do the 13. And that's going to give us 6.77. So I'm just going to write it down here. And then 6 times 13 equals 78. And then 88 minus 78 equals 10. And then 10 plus 6 carbons, it's going to be C6H16. But then we know that there's going to be an oxygen in here somewhere. So an oxygen has a molecular weight of 16. So that's equivalent to 1 carbon and 4 hydrogens, because carbon is 12 and then hydrogens are each 1. So 12, 1 carbon plus the 4 hydrogens gives us 16. So I can go ahead and subtract that from my molecular formula. So if I do minus 1 carbon minus 4 hydrogens, I would get C5H12O. And this will add up to our same molecular weight. And then we have, I'm recording something. Sorry, that was my roommate. Okay, anyway. Okay, where was I? All right. So percent oxygen, let me just erase this here. Subtract 100. I'm not going to write out all the math because you guys know how to do that. This is going to be just 66 or 68.1 plus 13.7. Okay, so that's going to give us 18.2. So that's the percent of oxygen that we have. And then, all right, C5H12O. We can look at we know there's an alcohol, so we already have the functional group, and there's only 1 oxygen in the compound, so there's really only one place it could be, and that's right there. There's a few CH-sp3 stretches right here, and then we have this 1 CO, which is from our alcohol. And calculating the du, let's do 5 minus 6 plus 1 is going to give us 0. All right, and then 6, 7, 8, 9, 10, 11, 12. So this matches up to our amount of hydrogens. We can make our little table. guys are probably getting the idea. They're all pretty much the same process. 1.7 and 3.6. Okay. So 6, 2, 1, 1, 2. This is going to be our 2 methyl groups. So I'll just do and as you can see the pattern here, usually you can just look at this integration and tell like, okay, 2H is going to be a CH2, 1H is going to be a CH, 6H is going to be 2 methyls. Once you do this more, you'll kind of get the hang of it and not really have to think about it too much. This right here, this 1H, it's so this peak is very how do I explain it? Like straight, I guess. Normally when you see an individual peak like this, we know there's an alcohol in here and it's further to the left. That's going to show us the electronegative atom, and that's going to give us the oxygen right there. And then this last one is our CH2. So this CH2, because it's so far to the left, it's going to be closer to the more electronegative atom. So this CH2 is probably going to be pretty close to this alcohol right here. So that's a good hint. The further to the left on the NMR you see the peaks, the closer to an electronegative atom it's going to be. So let's say we've got 2 carbons, 3, 4, 5, and it was 5 carbons total, so that works out. And then we've got our 6. Okay, we already counted the hydrogen, so we know that works. Now we have all of our puzzle pieces. Let's go ahead, since I know the alcohol is going to be on the end, and I know it's going to be attached to this CH2, I can just put that piece together like that. And then all we have left over is this middle piece, the CH, and then the CH2 over here. So these two, because these 2 methyls we know we're going to be on the end. So I'm going to put my CH2 here, and then CH, CH3, CH3. All right, so we can check this with our spin-spin coupling. We've got the doublet from these methyls, which works out because this is going to be a doublet. And then the CH2 has 1, 2, 3 neighboring hydrogens. So that's going to be a quartet, which looks like it is. So that checks out. This CH2 is a triplet, and it has these 2 here plus 1, so that makes it a triplet. And remember, you don't count this hydrogen because you don't count the hydrogens that are attached to an electronegative atom. So think of this oxygen like a wall. It only counts for the hydrogens on the neighboring carbons. So this molecule, it checks out with the spin-spin coupling. We can check it with the carbon NMR. We have 4 peaks here. We have 4 equivalent carbons, 1, 2, 3, 4. That works out. So then I can go ahead and rewrite this up here. I think it C5, was it H 12? O, and then Du of 0. I think it looks like that. Or maybe there's another carbon in there. All right. Yeah, okay. All right. So that's how you go about doing it. I would say for this unit, the biggest thing you can do is just practice. Just practice as many combined spec problems as you can. That's really the best way to learn it, because once you do it more and more, you'll start to notice patterns and you can do it more quickly and you'll just get a better hang of it. It does seem like a lot all at once, but it's really just like putting together the pieces of a puzzle. That's how I like to think about it. So yeah. Good luck studying and hope this was helpful.